welcome back. In this lecture, we will have this lecture for about an hour. This lecture will be about special devices and also diode circuits. Last week, Professor Sharma talked about PN junction and other details. There are a variety of diodes which are used in all kinds of applications. We will look at a few of them. Now, we know that when you reverse bias a PN junction, you have a depletion capacitance, and this depletion region, the width of the depletion region depends on the reverse bias. Now, because of this, the capacitance Cj, which is the junction capacitance of a reverse bias PN junction, can be related to the reverse bias voltage by this equation, where Cj, which is the junction capacitance, is Cj0 by 1 plus Vr by V0 to the power m, where Cj0 is the value of Cj for 0 voltage, and Vr is the reverse voltage, V0 is built-in voltage, m is the grading coefficient. Typically, for a PN junction diode will be the order of 0.3 to 0.5. So, when Vr is equal to 0, you would get the same value. Now, this property of a PN junction is extremely useful. There are special diodes by the name Varactors, where this particular property is made use of. Now, Varactors you can think of as voltage variable capacitors, where they use this variation of the capacitance as a function of the reverse voltage. The only difference is they are optimized for this particular purpose. Therefore, the grading coefficient is made between 3 to 4, so that the capacitance variation is a strong function of the reverse voltage. Now, where do we use this? We are all familiar with the fine-tuned control in our radio and such devices, portable devices. And typically, if you take a radio, the main capacitance there, the variation is from 0 to 70 pf. When you change the station, you are actually going from somewhere between, say, about 10 to 70 pf. Now, we all have noticed why this fine tune and when this fine tune came to picture. Maybe about 20 years ago, if you had a radio, it was extremely difficult to tune to shortwave stations, especially at night, because the variation, the way you could choose a station at night, it was extremely difficult to choose. And that is why when companies came up with this fine tune. In a fine tune, what you are essentially doing is you are putting a varactor in parallel to the main gang capacitor, and by fine tune what you are doing is you are actually changing the reverse voltage, and that can be varied very smoothly. So, you would get variation in sub picofarad, which is impossible in the gang capacitor. Now, so varactors find extremely common use. So, today you would find this in almost not only in radios, you would find also in several function generators and all. And because of this variation of the capacitance through voltage, you could use this in lots of gadgets, and the variation is typically in the sub picofarad range. So, varactors you would find extremely useful in many electronic application, especially in RF kind of applications. And being a reverse bias diode, you would find that the impedance, when you put them in parallel, there is not much change. I mean, it does not affect the other capacitance much. Now, let us look at another special type of PN junction or a diode, which is a light emitting diode. Again, today light emitting diode is something very common. We find it almost everywhere in our mobiles, all kinds of gadgets today we are very familiar. Now two things, I am sure we would have wondered how do we get these different colors, and also what is the principle of these light emitting diodes. Now light emitting diodes, as the word diode says, they are also a PN junction, they are made of PN junction, but these are special, they are made of special semiconductors. Now semiconductors can be classified either as direct band gap semiconductors or indirect band gap semiconductors. Now this is based on the shape of the band gap as a function of the momentum k. Now in a direct band gap semiconductor, the conduction band minima and the valence band maxima, they occur at the same momentum. Now generally we draw the conduction band and valence band as kind of straight lines, but actually you would find them. So what we mean is, so in a direct band gap semiconductor, the minima of the conduction band and the maxima of the valence band, they occur at the same momentum, crystal momentum. Now therefore what happens is, when you in an indirect band gap semiconductor, the minima of the conduction band and the maxima of the valence band, they do not occur at the same values of momentum. Typically, to give you an illustration, it would, in a indirect band gap semiconductor, so the minima of the conduction band is here and the maxima of the valence band is somewhere else. Now in direct band gap semiconductors, we know that when you forward bias a diode, the carriers are injected, holes injected from the P region to the N region. Now what happens is, when these carriers, these minority carriers, they recombine with the majority carriers on the other side, and when they recombine, they release energy. Now in indirect band gap semiconductors, this release energy would be in the form of lattice vibration, or this is also called non-radiative recombination. But in direct band gap semiconductors, a sizable number of these recombinations result in radiative recombination, or they would generate photons. Now so this is the basic principle of an LED. Now what I have given here, some examples of direct band gap semiconductors with their band gaps in electron volt in bracket. Now most of these direct band gap semiconductors are kind of alloys, or let us say compounds. Now gallium arsenide is a very good example. It is a binary compound. It has a direct band gap with a band gap of 1.43 and so on. Another popular one is aluminum gallium arsenide. It has both direct and indirect band gap, 1.42 to 2.46. It can be varied by changing the mole fraction of aluminum arsenide and gallium arsenide. So this is a ternary compound. You have a material called indium phosphide, then you have gallium nitride, indium gallium arsenide and so on. There are several such direct band gap semiconductors. Now when the radiative recombination takes place, the emitted photon energy would be equal to the difference between the higher energy state E2 and the lower energy state E1. Now that can be equated by an equation E is equal to E2 minus E1, which will be HF or HC by lambda, where lambda would be the light emission lambda, C is the velocity of light. Now the peak emission wavelength lambda we can express in a more convenient way in terms of the band gap energy by the equation lambda is equal to 1.24 divided by Eg in electron volt. So we see that just by changing the band gap we can get different light. So this is how you get different colors. We know that the visible spectrum is from about 400 nanometers to about 700 nanometer. At 700 we have red, 600 to 700 you have red, and you have blue somewhere around 300 to 400. Now by changing Eg you can get different values. Now let us take an example of a material like aluminum gallium arsenide. By changing the mole fraction of aluminum arsenide and gallium arsenide you can get different band gaps. We will not go into the details of the technology. Now this is how you could, so you could choose different materials and you could get different colors. Now let us talk about another very special device, again a diode called a laser diode. Now there were days when laser diodes were very costly and they were not seen. Today it is something very common. All of us are very familiar with the pointer which we use for presentation, and it costs hardly 50 rupees, and interestingly it is made of a laser diode which emits light of about around 500 micro, almost 1 milliwatt, a huge amount of light. Now what is the difference between a laser diode and a light emitting diode? Both are diodes, both emit light. What is the difference? Now in the light emission in a light emitting diode is by what is called a spontaneous emission. The reason why they are called spontaneous emission is because the emissions are isotropic. We said that if you forward bias a PN junction made of a direct band gap semiconductor, because of recombination we said there will be photon generation. Now this can happen all over the device. So therefore it is not at one point, it is not focused, it is not coherent, and the phase also is quite random. That is why it is called a spontaneous emission. So in a LED, as you would have noticed in a LED display, you would see that the light is actually emitting from a much larger area if you look closely, and in most of the LEDs we would use as a display device, and there we want the light to be as dispersive as possible, and all of us are familiar with the standard LED, and you would see that the structure is made such a way that light is kind of diffuse. So there the purpose itself is to diffuse the light. Now there is another way to get photon emission. This is what is called stimulated emission. Now here what is done is the downward transition which is basically releasing of energy can be stimulated, can be triggered through another photon. Now if you do this, the emitted photon will also be in phase, and this is what is called stimulated emission. Now if stimulated emission has to happen, then you need to satisfy a condition called population inversion, whereby essentially what we are saying is the number of excited states on the higher energy band has to be much higher than the ground state. Now this can be the structure, device structure of an LED, and a laser diode is very different from this point of view. In an LED you just have a simple PN junction made of direct band gap semiconductor of the right band gap to get the desired color, whereas in a laser diode you need to do something extra to make sure that you have a huge amount of carriers, and also they are kind of confined to a very narrow region so that you can satisfy population inversion. So this is done through what is called heterostructure. Now if you have a simple PN junction which we are familiar with, they are called homojunction, which means they are made of the same material, P and N. You can also have what are called heterojunctions, where they are made of dissimilar materials with different band gaps. Now we will not go into the details of it. So in a laser diode you would make a PN junction, it is not just a PN junction, it will be a P plus N plus kind of structure, where you would have different band gaps and the adjoining materials will be slightly different, but they will be matched. Now, because of this you would have a huge amount of carriers kind of trapped in a very narrow region because of the band gap difference, and also interestingly they also would have different refracting index, because of which when you forward bias this particular junction, this huge amount of carriers are generated, and after a threshold value of current you have stimulated emission. So, if we look at the characteristic of an LED, and also if you look at the characteristic of a laser, they are different. Now, what we have here is the current versus light characteristic of an LED, which is almost linear. If you draw the similar characteristics for a laser diode, the difference would be in a laser diode you would see that till a particular value of current, which is called the threshold current, the device works like a LED. So, which means it has only spontaneous emission. Once it exceeds a certain amount of threshold, which means number of carriers, it would go into stimulated emission and you get a huge amount of light. Now, the major advantage of a laser diode, which is generally written as LD, is basically coherence. Now, when you talk about coherence, there are two types of coherence. One is called the spatial coherence, whereby what you mean is the light is now confined to an extremely narrow region, as opposed to an LED where we said the light is isotropic. So, it kind of emits from all over the place. Here, because of stimulated emission, the light is extremely focused. Again, we are very familiar with the pointer which we are talking about, but in a pointer you also have a lens inside. You have another type of coherence which is called the temporal coherence. Now, temporal coherence is the word used for the spectral purity of the light. In an LED, if you see, even though you see a light as red, if you look at the spectrum of the light, you would see that in an LED, if you plot lambda on the x axis, in an LED you would see that the spectral width is quite large. Now, if you do the same thing in a laser diode, you would see that the laser diode spectrum is extremely sharp, meaning the light emits in an extremely narrow range of lambda. Now, this is what is called temporal coherence. Now, because of this, laser diodes are extensively used in several applications. LEDs are used in applications such as optical links, especially short range optical links. Today we are familiar with LAN. Most of the LAN applications would use an LED, because LED is a very cheap device, and the LED which is used for LAN is not the one which we are familiar with. They emit light in the infrared region, but the principle is very similar. Whereas laser diodes are used in optical fiber communication. Today in our country, optical fibers are used for communication throughout in all kind of telecommunication application. So, that is the difference between LED and laser diode, which are very similar. Now, let us talk about another type of device, which is a photodetector. Again, photodetector is very similar to, let us say, a solar cell. The main difference in a photodetector, you would reverse bias. This is again a PN junction, which is you would use in a reverse bias mode. Now, what happens in a reverse bias, when you reverse bias a a PN junction, any radiation, temperature or any radiation would affect its reverse bias current. Now, that is the principle of a photodetector. In a photodetector, the junction, the reverse bias junction is exposed to light, and the light energy, photon energy would be sufficient to break covalent bonds, which would result in what are called photocurrent. Now, in a photodiode, when you do not shine any light, you have a current which is called dark current, which is essentially the reverse saturation current, as opposed to what is called a photocurrent, which is a light, which is the current which falls due to light. Now, dark currents are typically extremely small, maybe nanoamps kind of range, and photocurrents can be, it depends very much on the amount of light you shine. Now, a photodetector can be thought of as a controlled current source. This is because of the reason that you have a reverse bias PN junction which has very high impedance. Now, because of this, we can model this more appropriately as a current source. Now, there is another very interesting device which you can form out of an LED and a photodetector, which is called an optocoupler. Now, optocoupler is an extremely useful device where this is nothing but a combination of LED and a photodetector. LED is essentially an electrical to optical converter, whereas a photodetector or a photodiode is an optical to electrical converter. There are situations where you would like to pass signal from one system to another system, but unfortunately you cannot connect a wire between these two systems because the ground potential of these two systems may be very high and there can be damages. This is very, very true if you are trying to take a signal from, let us say, a big vibrator or a vibrating equipment, let us say in a mechanical engineering lab, and you try to connect that signal to a PC. If you do that directly, your PC will burn immediately. In such a situation, what is done is you would use an optocoupler where you want to connect, take the signal from the instrument without directly touching. Now, an LED, we know that would give you a light which is proportional to the current flowing through it. So, if you apply a signal, it will give you a light which is proportional to the signal, and the photodetector, we again know, it would give you a current which is proportional to the light. So, at the output of the photodetector, you could take it, maybe amplify it, and you have a signal. And it is an extremely useful device which is used for achieving electrical isolation between two systems. And there are many practical applications where you cannot take signal from one system to another system through a wire. In such systems, you can use optocouplers, and very easy to make an optocoupler in a lab. Just you need to just paste, maybe just tie together an LED and a photodetector, and you could do very interesting experiments. Now, when we talk about diode circuits, so we talked about three types of diodes, special diodes. We talked about Varactor diodes, we talked about LEDs, we talked about laser diodes, we also talked about photodetectors, and then we talked about an application where you would use both photodetector and an LED, and we said it's an optocoupler. Now, diodes, we are all familiar with. The most popular and the most common use of a diode is it's used as a rectifying device, and we are familiar with both half wave rectifier and full wave rectifying applications. We will spend a little bit time on wave shaping circuits, which is another very major application of diodes. Now, very often you can think of a scenario that you have a sine wave signal and you want to get a square wave out of it. How do I do it? Now, one way is to use a comparator, maybe an op amp and so on, and you see that the moment you talk about an op amp, you are talking about more complication, power supply and so on. Now, this is something you can achieve easily using diodes or diodes. So, wave shaping circuits have kind of family of circuits where you would use the property of a diode and you would combine them with kind of your applications. Now, before we look at some simple wave shaping circuits, let us look at diode models. Now, there are different diode models exist, all of them assume diode to be an open circuit for reverse bias. Now, they all differ in the way the forward bias region is modeled. Now, we have one model which is called the exponential model, which is a very accurate model, which essentially uses the diode equation. Now, there are applications where you might like to determine the diode current very accurately. For example, one such circuit is shown here. Now, if you connect a power supply and a resistor, a series resistor, connect a diode. Now, how do I find out ID and VD? Unfortunately, we can write only one equation here, and there are two unknowns. ID and VD are both unknowns, but you can write only one equation here. Now, this is a scenario where we can solve this in two ways. Either you can solve it graphically, or we can solve this iteratively. Now, the exponential model would solve this either in graphical way or iteratively. Now, it is very easy to solve it iteratively, and we would get very accurate results. For example, in the previous circuit, we can write an equation, we can write the equation for the current through the diode as ID is equal to IS times e to the power Vd by Vt, where Vd is the voltage across it, the forward bias voltage across it, Vt is the thermal voltage. And from the same circuit also, applying KVL, Kirchhoff's voltage law, we can write current Vd as Vb, which is the input voltage, minus diode voltage by resistance. Now, we could solve this iteratively. Let us just take an example and see how quickly we get the result. Now, initially, let us assume that the battery which is given to you, power supply given to us has 5 volts, resistance is 1 K, and Is is 10 power minus 12 amps, and Vt is 25 millivolt. Now, we wrote the first equation where we wrote the equation for the diode current. From there, we can write the equation for Vd, the diode voltage, as Vt ln Id by Is. Now, initially you could assume Vd to be 0. That would give you the maximum current to the circuit. So, that current Id can be Vb by R1, which is 5 milliamps. Now, you could substitute that back into the equation for Vd. So, Vd will be then Vt ln 5 milliamps by Is. This will give you 558.3. Now, let us see how quickly the equations converge, and that shows the beauty of this method. In the second iteration, you could use this particular voltage as the diode voltage, recalculate, find Id again as Vb minus Vd. In this Vd, substitute 0.5583, and if you do that, you get the current to be 4.44. Earlier the current was 5 milliamps, now it has become 4.44. Now, you recalculate, find Vd, you would get Vd to be 555.4. You see how close it is to the previous result. Now, do the third iteration. Interestingly, the third iteration gives the same value, which means in just 2 iterations you got the exact value. This method is quite accurate, but unfortunately it is not very useful in a diode circuit, because most of the time you are not, you do not want to get this much accuracy. You are interested in a reasonably accurate model, but one which makes the analysis faster. Now, this is where we have about 3 models. The commonly used diode models are piecewise linear model, which has fairly good accuracy, and that is the model which is used most commonly. Now, in the experiment which we will be doing today afternoon, you would be using this. The handouts which are given to you gives you very detailed analysis of the circuit. Now, in the piecewise linear model, what you assume is, you assume linear IV characteristics. We know that the IV characteristics is exponential, but here you would make an approximation. You assume it to be linear, and you would see see that if you choose a proper value for the resistance, the approximation you would see that is fairly accurate. So you can think of here the exponential curve is approximated by two straight lines, one which is before the threshold point with a slope 0, and the second line with a slope of 1 by Rd, where Rd would be the diode forward resistance. So the piecewise linear model equations would be when Id is equal to 0, Vd, so that is the situation where Vd is less than Vd0, which is the threshold voltage or the voltage which you consider beyond which you consider it to be conducting, and Id will be Vd minus Vd0 by Rd, provided your Vd is greater than Vd0. So you have these two equations for these two lines. Now for signal diodes, which you typically use in the lab, the Vd0 is typically 0.7 volts and Rd would be somewhere between 10 to 20 ohms. Now remember, these values would change drastically depending on what type of diode you use. If you use a diode like IN 4001, which is a rectified diode, you would see that this resistance value would be much smaller. The reason is IN 4001 has a rating of 1 amp and 1000 volts PIV. So therefore, it is meant for that kind of an application. Therefore, you would see that the resistance is very small. But as signal diodes, which are meant for applications up to several higher frequencies, you can use it almost up to about 1 megahertz, whereas these IN 4001 you cannot use beyond, let us say, about 1 kilohertz. They have very large capacitance. So the forward voltage which you would get for an IN 4001 would be very different from the parameters you would get for a signal diode. Now what we have here is a quick simulation or a quick graphical way of showing how accurate the piecewise linear model is, and you see that the white curve here gives you the diode equation assuming Is to be 10 power minus 15 amps, and the other one you have 0.7 volts as the forward drop, and beyond up to 0.7 volts you have a line with slope 0, no current, and beyond that you have a line with a slope 1 by Rd, where your Rd is 10 ohms, and you see that this particular model is fairly accurate. So it all depends on the point you choose and also the value of the resistance you use. Now in a lab, once you are able to get this IV characteristics, you could choose two currents. So you could choose two currents on the y axis and find, if you expand your CRO and make a proper reading, you could get the difference in the diode voltage there, and from that you can get a fairly good estimate of Rd. That is how you would measure. If you want to model it properly, that is how you do in the lab. Now you have another model which is called the constant voltage drop model. Here you would assume that the diode is essentially an ideal diode. So you would assume that in the forward region, once it conducts, you would assume that it has a constant voltage drop of 0.7 volts, and there is no series resistance. Now this is a popular model from the point of view of analysis, because this makes analysis much simpler. If you have the previous model, which is the piecewise linear model, then it might require a few computations, whereas this is much simpler. Let us have a look at how accurate or how this particular model would compare with the actual scenario. So if you compare the constant voltage drop model with the actual scenario, you would get something like this. So here you see that this is a very let us say crude approximation, and still in spite of that it is still used for the sake of convenience. You also have another model which is called the ideal diode model, where you would assume that when the diode is forward biased, you will assume that the forward drop is 0, and the diode is also assumed to have 0 resistance. Now this is used in circuits, especially let us say when you talk about a rectifier circuit, you would generally ignore the diode drop. The reason, the argument there is that in a rectifier kind of application, the input voltage is much higher than this 0.6 or 0.7. So there it is well justified. So all these 4 models are used depending on the kind of application we have in mind. Let's try to apply this particular some of these models here. Now what we have here is basically we are using a ideal diode model here. We have a clipping circuit. So essentially we are applying a 12 sin omega t as the input here. We have a 1K series, and you have a diode here where we want to assume this diode to be ideal, and you have a power supply connected in series with the diode here with 3 volt, and you have the positive terminal here, negative terminal here. You have a 3K resistance of the load. Now how do we go about this? Now in such a circuit, what we generally do is to see the scenario where the diode, you split that into at least 2 scenarios. One scenario where the diode conducts, other scenario where the diode does not conduct, and then arrive at it. So we know that the way the diode is conducted, we know that for Vs positive, we know that diode cannot conduct. Now so therefore the output would be, in this particular case, would be 0.75 Vs. Now once you make Vs negative, because of that we can apply KVL, and we can write the current there as I. You can apply KVL here. So the current moving towards the node is I and I1, and you have I2 leaving the node here. So you can write I as I2 minus I1, and you could, for when the diode is conducting, I would be greater than 0. From that you could simplify, and you would see that the only when diode voltage, rather the input signal is less than minus 4 volts, the diode conduct. So in summary, we would have in this particular case, using the ideal voltage, ideal diode model, V out will be minus 3 volt provided Vs is less than minus 4 volts. That is the situation when D is on, and it will be 0.75 Vs when Vs is, I am sorry, here this should be greater than minus 4 volts. Now the scenario here is simulated here. So the white waveform here is the input here, and the red graph here is the output. Now you see here that the output voltage here, you can see it's clipped, and you have a flat line. If you perform this experiment in the lab, you would see that you never get such a flat line. You might get it depending on the value of resistance you choose, but for most of the values you would use, you would see that this would be a kind of you would see a small variation of the sign here. This you can get if you use the piecewise linear model, which is given in your handout. So if you do that, you would be able to get a fairly accurate estimation of what you are actually going to see. Now again, sinusoids have been already discussed. Here we will look at sinusoids from the point of view of their use in clipping circuits. Now as we know, sinusoids are reference voltage regulators. Now you could use them, especially there are, if you want to get Now, if you use a sinusoid kind of a back to back like this, and if your input is sine, assume that let us have a 10 sin omega t here, and we assume these to be 6 volt sinus, and if you assume the diode drop, the forward diode drop to be about let us say 0.6 volts, then what you would get at the output would be a kind of a clipped sine wave with a plus 6.6 and a minus 6.6. Now, in most applications, this kind of a square wave would be sufficient. In case we want only positive side, we could just use one of them. Now, coming to another the other applications, another popular application of a diode is what is called a clamping circuit. Here you would use a diode in series, a diode and a capacitor in series. Now, the circuit which is shown here, we have an input as Vm sin omega t, we have a capacitor here and a diode here. Now, the way the diode is connected, we know that it will permit only current to flow only in the direction from the top to bottom. Now, what will happen is, as the current flows through the diode that will charge the capacitor, with the result that the capacitor would get charged to the maximum voltage of the input. So, in this case the input is Vm sin omega t, therefore, the capacitor will get charged to Vm. Now, what happens is, at the output side, now since we have Vm here with positive here, negative here, and the polarity of the capacitor voltage is positive this side and minus here, you see that the output here would be nothing but Vm sin omega t minus Vm. Therefore, we would see that the output would be shifted to the negative side, and another way of arguing is this way. You see that the way the diode is connected here, we know that this output cannot be positive. So, in one sense we can think of this circuit adjusting itself such a way that the diode charges this capacitor and the output never becoming positive. Now, clamping, if you connect the diode the other way, we would have a scenario where the capacitor gets charged in the other polarity and the waveform getting shifted up. Now, these are very useful circuits. These kind of circuits are very commonly used in what are called DC restoration circuits, where you could restore the DC level. There are other applications such as voltage doublers, where you can use a clamping circuit and a rectifier circuit together. Now, in this case, what we have here is the same circuit where we have the diode connected in this fashion. So, with the result that the capacitor gets charged in this fashion, and we said that the voltage here would be negative, will be negative, and what we have here is basically a rectifier, a half wave rectifier, and this will conduct only in this direction. So, the output, the polarity shown here is wrong here. So, you will have minus 2 Vm here. So, these circuits are very useful, especially voltage doubler circuits are used in oscilloscopes and also in television sets, where you need to have very large voltages, especially the plate voltage in a CRO or in a television requires voltage of the order of 10,000s. So, their voltage doublers are very useful. This circuit, the moment you put a resistor, you would see that the voltages slightly change, and in most of the voltage doubler applications, the current drawn would be very small. Now, we could spend little time on simple rectifier circuits, especially the use of a capacitor in a rectifier. Now, rectifier circuit if you consider a half wave rectifier, and if you have a load here, and if the input is Vm sin omega t, now if we did not have the resistor there, then the capacitor would have, if the input was this. Now, if we did not have the resistor there, then the capacitor would have got charged to the full Vm here. The moment we put a capacitor here, and the resistor here, both charging and discharging takes place. Now, this is one of the common circuits used to get a DC voltage, and one of the common misconception is the method to reduce the ripple voltage. Now, in this case, what happens is the capacitor would charge, and because of the resistor it would discharge, and during the next positive half cycle it will charge, and so on. Now, very often it is thought that we know that the ripple, the peak to peak ripple here can be decreased by increasing the value for a given RL. If we, for a given RL, we can decrease the ripple by increasing the capacitor. So, that is very commonly thought as a way of reducing the ripple. But one very important thing to remember is not only the voltage at the output, but also the diode current. Now, the diode in this particular case, in the circuit shown here, the diode can conduct only for a extremely short period. Now, the entire charge or the entire voltage, the charge which was discharged through the resistance has to be picked up through the small interval through which it is charged, the charging period. Now, if you increase the value of the capacitor, this time period will keep reducing. The ripple will definitely decrease, will become much smaller, but the same way the peak current would keep increasing. Very often there are situations where a diode, maybe an IN 4001, which is used for an application like say 100 milliamps, you all of a sudden find that the diode has packed up, diode has burnt, and one really wonders why it burnt. And the answer is, if you put a small series resistance and try to monitor the diode current, we would see that the peak diode current is most of the time about at least 10 times the current that is flowing through the average current flowing. So, this is something which is to be kept in mind very often. So, in a power supply, therefore, the solution is to reduce ripple. The solution is not to put a large capacitor, rather to put some reasonable value like 1000 microfarad or so. The solution is to use voltage regulators. Now, to give a small recap of what we did in this particular lecture, let me just spend another 5 minutes quickly to recap what we did. We talked about special devices, we talked about varactors, we talked about them being used as kind of voltage controlled kind of capacitors. We said that they are very useful in not only appliances and in radio, especially in fine tune, and today we would find this very often. And the principle there is that of a PN junction, a reverse bias PN junction, which the capacitance changes with the reverse bias voltage. Then we talked about light emitting diodes. We said that they are again PN junctions, but these PN junctions are made of special semiconductors which are called direct band gap semiconductors, and the crystalline silicon which we are familiar with, the silicon is not a direct band gap semiconductor, and there are materials like gallium arsenide, aluminum galvanide, and many such materials. If you make a PN junction out of these materials, then when you forward bias this particular diode, you would see that they emit light, and this kind of phenomena is what is called radiative recombination. And we said that in some of these semiconductors you can change the band gap by changing the mole fraction, because most of them belong to, like especially the ternary like aluminum gallium arsenide or even quaternary. There, by changing the mole fraction, you can change the band gap, thereby you can change the lambda of the light emission. We also talked about laser diodes, where we said the process is what is called stimulated emission, where the light which is emitted is coherent both spatially and temporally, and they, to achieve population inversion, they use special structures which are called heterostructures, which are made of different materials with slightly different band gap but matched. And we said that LEDs are very commonly used even in communication, especially in small LAN applications, but laser diodes are the devices of choice, especially in optical fiber communication. And today in our country, all over the country, optical fibers are used as the backbone for all communication. And then we talked about photodetectors, which we said are nothing but PN junctions which are reverse biased, and also where the junction is exposed to light, and you would generally find photodetectors with kind of a quartz window, and they have what are called dark current, which is nothing but the reverse saturation current, and also have what is called a photocurrent, which is the current caused by light, and the photocurrent we said is directly proportional to the light falling on it. And we talked about another interesting device which we could even make it in a lab easily, which is what is called an optocoupler, which is made out of LED and photodetector, which we said can be used to couple couple a signal from one system to another system. When you talk about system, we are talking about maybe major equipment, maybe taking a signal from a very big equipment to a PC. In some kind of scenario, we cannot directly take, because the grounds may be at different potential, and this optocoupler is a device which helps us in such a situation to achieve electrical isolation. We also talked about different diode models. We talked about the exponential model, which we said is a very accurate model, and is very useful if you have a simple circuit and you want to find out the exact voltage and diode current. But we said unfortunately it is not very easy to use, and we talked about three more models. We said the piecewise linear model, where we assume a linear IV characteristics, and we said this particular model is an extremely accurate model, and when we fitted this with an actual characteristics, we found that the fitting was very good. And we also said occasionally we would use a constant voltage drop model to make our hand calculation simpler, and occasionally we might also use ideal diode model, especially in rectifier circuits. And then we talked about clipping circuits. We also talked about both synodiodes also being used in clipping circuits. We finally talked about clamping circuits and voltage doublers. So I would stop my lecture here.